And so basically I'm keeping track of all the information I need to know about the past. And so that I'm going to want to start in state 1, 1. So I'm going to start here. And I'm going to define my input to be E, and my output is Z, and this is x sub I, x sub I minus 1, x sub I minus 2 equals y sub I minus 1, y sub I minus 2. And the input's defined up there. So, I'm going to start here, and if I find out that the most current bits are not equal, basically that's going to make my next state that y sub I were not equal, but the previous two were. So this is going to, if I get a 0 here, I'm basically just going to shift these all over, so this becomes 0, 1, and my two 3-bit numbers are no longer equivalent. And if I get that they are equivalent, I'm going to stay in my equivalent state and output a 1. Now let's start here. So I'm in the 0, 1 state. If I find out that the current inputs are the same, I'm going to want to go to 1, 0. So if I get 1, and they're not, the two 3-bit numbers cannot be the same, so this will go to state 1, 0. And so this is not equal. So this the previous bit was equal, and the previous 2 bits ago was not equal. And if I get a 0, that's going to need to go across to here, to 0, 0. Basically, the last 2 bits were no longer equal. And now I've got 0, 0 here. This will send me to, so let's do this one first. 1, 0. If I get a 1, that's going to send me to here. And this has 1 and basic. So that's saying I've now found 2 bits in a row, so that's still not, they're equal. And the 0, so if I get, this will send this back up to here. So this is 0 / 0. And if now I've got this one, so if I find out that there's again not equal, this is going to stay put. So 0 / 0. And if I find out that the first one is equal, then it goes back to here. So 1 / 0. So that's my state diagram. And now I just need to design. So I've already got E, and now I just need to find out what Q1 and Q0 are going to be. And we will need X, Q1, Q0, 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. And then we're going to have Q1 plus Q0 plus and Z. So if we're in state 0, 0 and we get 0, we're going to stay in 0 and output 0. If we get if we're in state 0, 1 and we get an input of, oh sorry, this should be X, this should be E. So if I get an input of 0 and 0, 1, I'm also going to go to 0, 0 and output a 0. And now I've got, I'm in state 1, 0, and I've got an input of 0. So that is going to go to 0, 1. And my output is going to be 0. Now I've got 0, 1, 1. So 1, 1, and I get a 0. I'm going to go to state 0, 1. And now I've got 0, 0, and I've got input of 1. So that's going to send me to 1, 0. My output again is going to be 0. If I'm in 1, 0 and I get a 1, if I'm 0, 1 and I get a 1, that's going to send me to 1, 0. And my output's going to be 0. If I'm in state 1, 0 and I get a 1, that'll send me to state 1, 1 and I should output a 0. and if I'm in state 1, 1, and I get a 1, that's going to keep me in 1, 1, and I'll finally get an output of 1. So just glancing at this, I see that Q1 plus is equal to E, Q0 plus is equal to Q1, and Z is equal to E, Q1, Q0. And that actually completes the design, and I do not need to draw the circuit, although if you just take a quick look at this, this is just a shift register, and this is just ANDing the the input after the X NOR gate with the two flip-flops outputs at Q. And that completes this problem.